280 million years after the Big Bang, a galaxy was already shining brightly enough for James Webb to find it. MOMS E14 should belong to an age when cosmic structure was only beginning to assemble, yet it is part of a growing pattern. Unexpectedly luminous galaxies, mysterious little red dots, and black holes gaining enormous mass far earlier than many models anticipated. Webb has not broken the Big Bang. It has revealed that the young universe may have been far more efficient at building stars, galaxies, and black holes than expected. If these calm journeys into deep space are worth returning to, liking, subscribing, and sharing helps calm space science continue creating them. And wherever this signal has reached tonight, leave a comment with the city or country you are listening from and what time it is there. Thank you for spending part of your time here. The first ancient photons are already arriving, and their story begins at the edge of Webb's deepest view. James Webb Space Telescope does not look into the past by crossing time in any ordinary sense. It does something quieter and more physical. It receives light that has been travelling for so long that the objects which produced it may have changed beyond recognition, merged into larger systems, or disappeared entirely by the time that light reaches the region of space where Earth now moves. Every distant galaxy is therefore seen not as it is now, but as it was when its photons began the journey. The farther those photons have travelled, the earlier the moment being observed. This simple fact is the foundation of deep space astronomy, and it turns the sky into a layered record of cosmic history. Nearby stars appear almost current on astronomical timescales. Galaxies millions of light-years away are seen millions of years in the past. At still greater distances, the delay stretches across billions of years, until observation begins to approach epochs when galaxies themselves were young. Webb was designed for this regime. Its large primary mirror gathers extremely faint light, while its instruments are optimized to detect infrared radiation, the portion of the spectrum that becomes especially important when the universe is observed across immense stretches of space and time. The reason lies in cosmic expansion. Space is not a static stage through which galaxies simply move. On the larger scales, the fabric of the universe expands, increasing the distance between widely separated regions. Light travelling through that expanding space is stretched along with it. Its wavelength grows longer as the universe expands during the journey. So radiation that began in visible or ultraviolet wavelengths can arrive shifted into the infrared. Astronomers describe this stretching as redshift. The greater the redshift, in general, the more the light has been stretched, and the earlier the observed object is being seen. Redshift is not merely a colour change. It is a measurable imprint of cosmic expansion, and one of the central tools for reconstructing the history of distant galaxies. Webb is exceptionally powerful because it was built to detect precisely the long wavelength light that the early universe sends into the present. A young galaxy may have produced intense ultraviolet radiation from hot, short-lived stars. Yet by the time that radiation crosses most of the observable universe, expansion can shift it far beyond the ultraviolet and visible bands. An optical telescope can then face an odd situation: the object exists within reach of the observable universe, but much of the light that carries its strongest signature has moved out of the wavelengths the telescope is best equipped to see. Infrared observation restores access to that information. It does not make Webb magically see through all barriers, and it does not allow the telescope to look all the way to the instant of the Big Bang. It allows Webb to follow the redshifted light of early stars and galaxies farther back than previous observatories could do with the same sensitivity and spectral detail. That distinction matters, because the phrase looking deeper into space can sound like a matter of magnification alone. It is not. Webb's reach depends on collecting power, wavelength coverage, low instrument temperatures, long exposures, careful calibration, and the ability to separate extremely weak astronomical signals from foreground light and detector noise. The telescope operates far from Earth in a stable region of space, protected by a large sunshield that keeps its observatory side cold. That cold environment is essential for infrared astronomy. Warm objects emit infrared radiation, including telescopes themselves. So an infrared observatory must suppress as much of its own heat as possible if it is to detect faint signals arriving from the distant universe. The engineering and the cosmology are therefore connected. Webb can study the early universe because its mirror, instruments, orbit, thermal design, and observing strategy were all built around the problem of collecting ancient, red-shifted light. Even then, distance is not read directly from brightness. A faint object may be far away, but it may also be intrinsically dim. A bright object may be distant, or unusually luminous, or magnified by gravitational lensing from matter lying in front of it. Astronomers need the spectrum of the light, not brightness alone, to establish a secure picture. When light is spread into its component wavelengths, patterns produced by atoms and by sharp changes in a galaxy's emission can reveal how far those patterns have shifted from their known rest wavelengths. This produces a spectroscopic redshift, one of the strongest ways to confirm that an object truly belongs to the very early universe, before spectroscopy is available. Astronomers can estimate distance using photometric redshift, comparing how bright a source appears through different filters. That method is extremely useful for finding candidates across large surveys, but it carries more uncertainty. A dusty or unusual galaxy at a lower redshift can sometimes imitate the colors expected from a much more distant object. Webb's power therefore comes not only from discovering faint red points, but from testing what those points actually are. Its imaging instruments can identify candidates that appear to lie at extraordinary distances, and its spectroscopic instruments can then examine the light in greater detail. This movement from detection to confirmation is what converts an intriguing source into evidence about cosmic history. At the highest redshifts, even the basic act of seeing a galaxy becomes a reconstruction. The image on the detector is not a photograph in the ordinary sense. It is a map of photons that have survived a long journey through expanding space, intergalactic gas, foreground structures, and the limitations of the instrument itself. Their wavelengths encode the expansion they experienced. Their brightness carries information about the stars, gas, dust, and possible black hole activity within the source. The distribution across the image reveals shape only after careful processing. The result can appear simple, perhaps only a small patch of light, yet that patch may represent a galaxy observed when the universe had completed only a small fraction of its later history. This is why Webb's deepest observations have such unusual scientific weight. They do not simply add more distant objects to a catalogue. They reach into a period where the familiar architecture of the cosmos was still assembling. Galaxies were gathering gas, forming stars, enriching themselves with heavier elements, and interacting with the radiation that filled the space around them. Every confirmed step toward higher redshift narrows the gap between direct observation and the still earlier era when the first luminous structures began to appear. There is, however, a limit built into the nature of light itself. The early universe was not always transparent. Before atoms formed and radiation could travel freely over great distances, matter and light interacted too strongly for ordinary telescopes to see through that earlier plasma. Webb is not designed to penetrate beyond every cosmic boundary. Its role is different. It is pushing direct observation into the era after the universe became transparent, and toward the later period when stars and galaxies first began reshaping their surroundings. The deeper it looks, the more compressed the timeline becomes. A difference of what seems like a small amount of cosmic time can correspond to a major change in what kinds of structures should exist. This is where redshift becomes more than a distance marker at modest distances. Moving slightly farther back may reveal galaxies that are somewhat younger. Near the cosmic dawn, the same observational step can move into an epoch when an entire stage of galaxy formation may not yet have had much time to unfold. A galaxy found there is therefore judged not only by how far away it is, but by whether its brightness, mass, chemical state, and structure make sense for such an early date. Webb's deepest fields are beginning to populate this thinly explored interval with real objects rather than theoretical placeholders. That is the source of the growing tension. The telescope is not simply seeing farther than Hubble because it has a newer mirror or sharper technology. It is opening a wavelength window in which the distant universe becomes accessible in a way it was not before. And with that access comes a more demanding comparison between models and reality. For decades, astronomers could simulate the first generations of galaxies in detail while observing only fragments of the period in which those systems emerged. Webb changes the balance. The models now face direct measurements from epochs they were built partly to predict. Some of those measurements fit comfortably, others do not. The first surprise, then, is not a single impossible object waiting at the edge of vision. It is the fact that a telescope designed to collect stretched infrared light can now turn the early universe from an inferred chapter into an observed one, and once that chapter becomes visible, its contents can be tested line by line. The universe that Webb is beginning to expose at extreme redshift is not simply a younger version of the modern cosmos. It belongs to a period when almost every familiar large-scale structure was still incomplete, when heavy elements were scarce. Galaxies were smaller and more unstable, and the first sustained sources of starlight were beginning to change the darkness around them. Astronomers call this broad transition the cosmic dawn. It does not refer to a single instant. It describes an era stretching across the first few 100 million years after the Big Bang, when the first stars ignited, the first galaxies assembled, and radiation from those objects began transforming the surrounding hydrogen. Before that transition, the universe had already passed through several profound changes. It had expanded and cooled from an extremely hot early state. Protons and electrons had combined into neutral atoms. Light had decoupled from matter and begun travelling freely across space. That ancient radiation survives today as the cosmic microwave background. But after its release, the universe entered a long period with very few luminous objects. Matter was present, gravity was acting, and structure was growing, yet the sky would not have resembled any later epoch filled with stars. Dark matter gathered first into gravitational wells, drawing ordinary gas toward regions of increasing density. Small differences in the distribution of matter slowly became larger. Gas accumulated, cooled, and in some places became dense enough for the first stars to form. Those stars are expected to have been unlike most stars seen nearby today. The early universe contained almost no elements heavier than hydrogen and helium, because elements such as carbon, oxygen, silicon, and iron had not yet been manufactured in significant quantities inside earlier generations of stars. The first stellar populations therefore formed from unusually simple material. Without heavier elements to help gas cool efficiently, large clumps could remain warm and resist breaking into many small fragments. So some models suggest that many of the earlier stars were more massive than typical stars in the present universe. Their exact masses remain uncertain, but their influence would have been enormous. Massive stars burn through nuclear fuel quickly, radiate strongly in ultraviolet light, and end their lives after relatively short periods, often enriching their surroundings with the first heavy elements. In that sense, The cosmic dawn was not only the beginning of widespread starlight, it was the beginning of chemical complexity on a cosmic scale. Every early supernova changed the material available to the next generation. Gas that had once contained almost nothing beyond hydrogen and helium began receiving the ingredients needed for rocky planets, complex molecules, and eventually the chemistry associated with life. Yet this transformation did not happen evenly. The early universe was clumpy. Some regions collapsed before others. Some dark matter halos became efficient nurseries for star formation, while neighbouring regions remained almost empty of luminous sources. The first galaxies likely emerged from this uneven landscape as small systems that repeatedly merged, accreted fresh gas, and underwent bursts of star formation. They were not miniature versions of the Milky Way. They were changing rapidly, often on timescales short enough that a galaxy could look dramatically different after a relatively small fraction of cosmic history had passed. This is one reason the cosmic dawn is so difficult to model. Gravity provides the large-scale framework, but the visible appearance of a young galaxy depends on many interacting processes. Gas must enter a halo, lose energy, collapse, and form stars. Those stars then heat and ionize nearby gas. Stellar winds and supernova explosions can push material outward, sometimes slowing further star formation and sometimes compressing other regions enough to trigger it. Black holes, if present, can add another source of energy. Dust can absorb ultraviolet light and re-radiate that energy at longer wavelengths. Even a galaxy with modest mass can therefore pass through phases of brightness that do not map neatly onto its total amount of matter. Before Webb, much of this era remained observationally thin. The Hubble Space Telescope pushed deeply into the early universe and identified galaxies from remarkably high redshifts, but its strongest sensitivity lies at shorter wavelengths than Webb's, and cosmic expansion shifts the most useful early galaxy signals progressively farther into the infrared. As redshift increases, galaxies that would emit strongly in ultraviolet light become harder for an optical observatory to characterize. Their light is faint, stretched, and altered by the hydrogen between the galaxy and the telescope. Hubble could reveal the approach to the cosmic dawn, but it could not survey its earliest phases with the same combination of sensitivity, wavelength coverage, and spectroscopy now available to Webb for years. This left an unusual gap between theory and direct observation. Astronomers could estimate when the first stars should form. Simulations could track dark matter halos, gas cooling, star formation, and feedback. Models could predict how many galaxies of a given brightness ought to exist at different redshifts. Yet the most remote end of those predictions remained only weakly tested. Webb was built in part to close that gap. Its infrared instruments can identify galaxies whose ultraviolet light has been stretched into wavelengths that earlier telescopes could not study as effectively. And its spectrographs can determine whether apparently distant objects truly belong to the cosmic dawn. This matters because the early universe is crowded with potential confusion. A nearby dusty galaxy can appear very red. Strong emission lines can distort the brightness measured through broad filters. An object that seems extraordinarily distant from imaging alone may move to a lower redshift once its spectrum is measured. Reliable progress therefore requires more than finding faint red sources. It requires confirming the pattern of wavelengths expected from a genuinely distant galaxy and separating that signal from lower redshift imposters. With that confirmation, cosmic time becomes much more precise. A galaxy observed only a few 100 million years after the Big Bang has had very little time to build stars, manufacture heavy elements, grow a central black hole, organize internal structure, and influence the space around it. Each of those processes has a physical pace. Gas cannot collapse instantly. Stars require time to form and evolve. Black holes require time to gain mass unless they begin from unusually large seeds or grow under unusually efficient conditions. Chemical enrichment requires repeated generations of stellar birth and death. The cosmic dawn is therefore a natural laboratory for testing how quickly these processes can proceed when the universe itself is young. It also marks the beginning of another transformation, one that affected nearly all of intergalactic space. After the universe cooled enough for neutral hydrogen to form, much of that hydrogen remained neutral for a long period. Ultraviolet radiation from the first stars, galaxies, and perhaps accreting black holes gradually stripped electrons away from hydrogen atoms again, a process known as reionization. This did not happen everywhere at once. Ionized bubbles likely formed around groups of luminous sources and expanded until they overlapped, turning the intergalactic medium from mostly neutral to mostly ionized. The timing and sources of this transition remain major questions. Cosmic dawn and reionization are therefore connected. The same early galaxies that reveal how structure assembled also help explain how the universe changed its physical state. Webb is now examining both sides of that story at once, the internal growth of galaxies and the effect their radiation had on the space beyond them. That dual view is what makes this period especially revealing. A galaxy at extreme redshift is not only an isolated object, it is part of a network of emerging structure, radiation, chemistry, and feedback operating when the universe was still establishing the conditions that later became normal. The earliest confirmed galaxies therefore carry more information than their faint appearance suggests. Their brightness constrains how efficiently gas turned into stars. Their spectra reveal the composition and ionization of their gas. Their sizes and shapes test how rapidly structure developed. Their number tells whether galaxy formation was common or rare at a given epoch. Their black holes, when present, test how quickly compact objects could grow, and their radiation helps trace the clearing of the neutral hydrogen that filled the young cosmos. Before Webb, much of this history had to be inferred from what came later. Now the sequence is beginning to acquire direct observational anchors. The cosmic dawn is no longer only a theoretical border between darkness and light. It is becoming a measurable landscape, and once objects can be placed within it with confidence, the question changes from when the first galaxies should have appeared to what those first galaxies were actually capable of becoming in so little time. MOMS 14 is important not because it appears large or spectacular in an image, but because its light reaches Webb from a time when the universe was only about 280 million years old. Its confirmed redshift of 14.44 places it among the most distant galaxies ever measured spectroscopically. And at that distance, the ordinary idea of seeing a remote object begins to merge with the problem of reconstructing cosmic beginnings. The galaxy is not being observed as an ancient relic sitting unchanged at the edge of space. It is being observed during an early stage of its own existence, when the universe had completed only a small fraction of the history that would eventually lead to mature galaxies, heavy element enrichment, planets, and the complex structures visible today. The photons detected by Webb began their journey so early that there had been little time for luminous matter to assemble. That is why a system such as MOMZ-14 carries more weight than its small appearance might suggest. Its existence becomes a constraint on how rapidly the first galaxies could form, how efficiently they could convert gas into stars, and how quickly enough stars could accumulate to make a galaxy visible across nearly the full span of cosmic history. Redshift provides the key. A value as high as 14.44 means that the wavelengths arriving at Webb have been stretched enormously by cosmic expansion compared with the wavelength at which the light was originally emitted. Radiation produced in the ultraviolet by hot young stars is shifted deep into the infrared by the time it reaches the telescope. Webb was designed for exactly this regime, but even for Webb, a galaxy at such a redshift lies near the observational frontier. The signal is weak. The object is extremely faint. The interpretation depends on separating genuine high redshift features from other sources that can mimic similar colours. This is why spectroscopic confirmation matters so much. Imaging can identify candidates by looking for the characteristic way their light appears and disappears across different wavelength filters. But spectroscopy tests whether the expected breaks and emission features are actually shifted to the positions required by such an extreme distance. When that confirmation succeeds, the object stops being merely a promising candidate and becomes a fixed point in the chronology of the early universe. MOMZ14 therefore extends a sequence that Webb has been building almost from the beginning of its deep field observations. Earlier discoveries had already pushed beyond the limits that were routine before Webb, including galaxies such as JWST 14-0, which showed that bright systems could be present at epochs once expected to contain fewer observable galaxies. Each newly confirmed source at higher redshift does more than replace a record holder. It narrows the remaining interval between the earliest galaxies directly observed and the still earlier period when the first stars must have begun forming inside small dark matter halos. That interval is scientifically valuable because the processes operating within it are changing rapidly. A difference of tens of millions of years near the cosmic dawn can represent a meaningful fraction of the time available for gas collapse, star formation, chemical enrichment, and galaxy assembly. Moving the observational frontier earlier therefore places increasingly strict limits on how quickly those processes must have started. The surprising part of MOMZ14 is not that cosmology forbids a galaxy from existing at that time. It does not. The standard picture of cosmic structure formation predicts that the first density fluctuations begin growing long before the first galaxies become visible, and some regions should collapse earlier than average. The tension comes from the brightness and apparent development of galaxies that are being found so early, and from how often such luminous systems seem to appear in Webb surveys compared with many pre-launch expectations. A very faint, primitive galaxy at this age would fit comfortably into many models. A galaxy bright enough to be detected and confirmed across such a distance demands a more specific explanation. It needs a sufficient supply of gas, a gravitational environment capable of gathering that gas, and star formation intense enough to produce the observed luminosity. If several such systems appear within modest survey volumes, the question becomes broader. The models must explain not only how one unusually efficient galaxy formed, but why the early universe seems capable of producing a population of them. This is where the record-setting language can obscure the deeper significance. The scientific value is not the competition for the highest redshift. It is the construction of a population across redshift. One galaxy establishes possibility. Several begin to reveal frequency. A sufficiently large sample starts to define the luminosity function, the statistical distribution of galaxies by brightness at a given epoch. That distribution allows astronomers to compare observation with models of dark matter, halo growth, gas accretion, stellar feedback, and the efficiency with which baryonic matter becomes stars. If the bright end contains more galaxies than expected, then some part of that chain may need adjustment. The universe may be converting gas into stars more efficiently in certain early systems. Star formation may occur in short, intense bursts that temporarily make young galaxies much brighter. Early stellar populations may produce more ultraviolet light per unit mass than later populations. Dust may be less abundant in some systems, allowing more ultraviolet radiation to escape. Selection effects and limited survey areas may also make early samples appear unusual until larger observations are available. None of these possibilities requires abandoning the broader cosmological framework, but each changes the physics of what the first galaxies were doing. MOMSI 14 sits directly inside that problem. Its redshift establishes when it is being observed, but the next questions concern what kind of object could become visible so early. Astronomers examine its spectral energy distribution, emission features, inferred stellar content, and the surrounding environment for clues. At such distances, every interpretation carries uncertainty because the source is faint and the available light samples only certain parts of its physical state. Stellar mass, star formation rate, age, and metallicity are not measured in the same direct sense as redshift. They are inferred by comparing observations with models of stellar populations and nebular emission. That means an apparently mature galaxy may sometimes become less extreme when assumptions improve. Webb has already shown the importance of this caution. Some early candidates selected from imaging have moved to lower redshifts after better spectroscopy, while other extreme objects have survived increasingly careful tests. The lesson is not that the first surprising results were wrong. It is that the frontier advances by repeated confirmation, revision, and replacement. MOMS 14 matters because it belongs to the more secure side of that process. Its distance has been established strongly enough to place it within the first few 100 million years, where the time available for galaxy building is genuinely short. The object also illustrates why Webb can continue pushing closer to the beginning, even without seeing the first galaxy immediately. Deep observations accumulate exposure time, improve candidate selection, and cover different areas of the sky. Gravitational lensing can sometimes magnify background systems, while blank field surveys reveal populations without relying on strong foreground lenses. Spectroscopy then turns the most promising candidates into chronological anchors. As this process continues, record redshifts are likely to move again. The significant question is how the properties of those galaxies change as the timeline is pushed earlier. At some point, the population should become smaller, fainter, chemically simpler, and more strongly dominated by newly formed stars. Eventually, the observations must approach an era before ordinary galaxies have had time to assemble in recognizable form. Where that transition appears will test how well current models capture the onset of structure. MOMS 14 is therefore less like a final boundary than a marker placed on a moving frontier. It says that by roughly 280 million years after the Big Bang, at least one galaxy luminous enough for Webb to confirm was already present. It also implies that the processes needed to create that galaxy began earlier still. Gas had to collect before stars could form. Stars had to form before their light could dominate the spectrum. The halo containing the system had to grow from smaller fluctuations that were already evolving in the preceding darkness. Every confirmed galaxy at this epoch therefore points backward to an even earlier chain of unseen events. That backward implication is what makes MOMSI 14 especially revealing. The telescope has not reached the first light of the universe, but it has moved close enough that the gap between visible galaxies and their invisible beginnings is becoming narrow enough to measure. The unexpected brightness of the earliest galaxies became one of Webb's first major pressures on existing models because it was not limited to a single remarkable object. As survey after survey accumulated, astronomers began finding more luminous galaxies at very high redshift than many pre-launch forecasts had suggested should be common. The discrepancy did not mean that the underlying cosmology had failed. It meant that the visible part of galaxy formation was proving more efficient, more variable, or more complicated than some models had assumed. Before Webb, predictions for the cosmic dawn were built from a combination of dark matter simulations, gas physics, star formation prescriptions, and the limited observations available from earlier telescopes. Those models generally agreed on the broad sequence. Dark matter halos would grow through gravitational collapse and mergers. Ordinary gas would fall into those halos. Some of that gas would cool, fragment, and form stars, radiation. Stellar winds and supernova explosions would then push back against further collapse, reducing the efficiency with which gas could continue becoming stars, in low-mass systems especially. This feedback was expected to be powerful enough to prevent most available gas from turning quickly into luminous stellar populations. The result was a young universe populated by many small, faint galaxies, with the brightest objects becoming progressively rarer at earlier times. Webb did find enormous numbers of faint systems, but it also exposed a bright tail that appeared richer than expected. Some galaxies observed only a few 100 million years after the Big Bang were producing enough ultraviolet light to stand out clearly despite their extraordinary distance. That brightness immediately raised a physical question. If the ultraviolet light comes mostly from young, massive stars, then either those galaxies are forming stars at very high rates. Their stellar populations are unusually efficient producers of ultraviolet radiation. Their light is escaping with relatively little obstruction, or some combination of these effects is operating together. Each possibility changes the interpretation of how quickly early galaxies evolved. Star formation efficiency is one of the most direct possibilities. A dark matter halo may contain a reservoir of ordinary matter, but only a fraction of that gas normally becomes stars. If early galaxies converted a larger fraction of incoming gas into stars than expected, their luminosities could rise sharply without requiring the halos themselves to be impossibly massive. The physical conditions of the young universe may have encouraged this in certain environments. Gas supplies were abundant, accretion could be rapid, and mergers were frequent. Dense streams of relatively cool gas may have penetrated growing halos and delivered fresh material directly into star-forming regions. If that gas was compressed faster than feedback could remove it, a galaxy could experience an intense burst of star formation before later processes slowed it down. Such bursts matter because astronomical surveys capture galaxies at particular moments. A system does not need to remain extremely luminous for a long time to enter a Webb sample. It may only need to pass through a brief episode in which large numbers of massive stars form nearly simultaneously. Those stars are exceptionally bright in ultraviolet wavelengths but short-lived. A galaxy caught during that phase can therefore look disproportionately luminous compared with its total long-term stellar mass. This introduces a form of cosmic timing into the observations. The brightest early galaxies may not represent a permanently different class of object. Some may be ordinary young systems observed during unusually active moments, but that explanation has limits. If bright galaxies are sufficiently numerous, then short bursts alone require those active phases to occur often enough across the population to match what Webb sees. The statistics of the surveys then become as important as the individual objects. Stellar populations add another layer. The earlier stars formed from material containing fewer heavy elements than stars in later galaxies. Low metallicity stars can differ in temperature, lifetime, and radiation output, and a population weighted toward relatively massive stars could produce more ultraviolet light for a given amount of stellar mass. In the most extreme theoretical case, the first generation of nearly metal-free stars, often called Population 3, may have been unusually massive and luminous, although directly identifying such stars remains difficult. Even without a purely primordial population, young metal-poor stars could make early galaxies brighter than models calibrated mainly on later cosmic epochs might predict. The amount of dust also matters. Dust grains absorb ultraviolet and visible radiation and re-radiate the energy at longer infrared wavelengths. In galaxies that have undergone many generations of star formation, dust can hide a substantial fraction of young stars. The earliest galaxies have had less time to manufacture heavy elements and dust, although some evidence shows that dust production can begin surprisingly quickly. If many high redshift systems contain relatively little obscuring material, more of their ultraviolet light can escape directly into intergalactic space. Webb would then detect galaxies that appear very bright not because they contain extraordinary amounts of stellar mass, but because a larger share of the light produced by their young stars reaches the telescope. None of these explanations acts independently. Gas inflow determines the fuel supply. Star formation controls how rapidly that fuel becomes luminous stars. Stellar populations determine how much radiation is produced. Dust controls how much escapes. Feedback from stars and black holes regulates what happens next. A galaxy can move through these conditions quickly, making the relationship between total mass and observed brightness far less stable than a simple model might assume. This complexity is one reason early claims of impossibly massive galaxies required careful revision. Some of the first Webb candidates appeared, from their colours, to contain enormous stellar masses at surprisingly early times. Better data and improved modelling reduced the inferred masses of several systems. Strong emission lines could boost certain infrared filters and imitate the smooth light of an older, more massive stellar population. Dust could alter the colours. Active black holes could contribute light that might otherwise be attributed to stars. Photometric redshift uncertainties could place an object farther away than spectroscopy later supported. These effects showed that brightness could not be translated directly into mass. Yet correcting the most extreme initial estimates did not remove the broader pattern. Webb continued to reveal a surprisingly active early universe. Spectroscopically confirmed galaxies at very high redshift remained luminous enough to require rapid star formation, and deep surveys continued to find more bright systems than some models had predicted. The tension therefore shifted rather than disappeared. The question was no longer whether the universe contained galaxies that violated basic physical limits. It became how ordinary physical processes could operate with enough efficiency to produce so much observable light so soon. That is a more subtle problem, but it may ultimately be more useful. A genuine contradiction would simply indicate that a model was wrong. A systematic mismatch in brightness provides clues about which ingredients may be incomplete. Simulations can change assumptions about how gas enters small halos, how quickly dense clouds turn into stars, how efficiently supernovae eject material, how often galaxies undergo bursts, and how luminous metal-poor stellar populations become. Each change leaves different observational signatures. Stronger star formation efficiency should affect stellar masses and growth histories. Bursty star formation should create rapid variations in luminosity and distinctive stellar age distributions. Reduced dust should alter spectral slopes. Unusual stellar populations should influence emission lines and the production of ionizing radiation. Black hole activity should introduce its own spectral features. Webb can test these possibilities because it does more than count galaxies. Spectroscopy allows astronomers to examine the physical conditions inside them. Emission lines reveal excited gas. Continuum light constrains stellar populations and dust. Different wavelengths help separate compact nuclear sources from widespread star formation. As samples grow, these measurements can determine whether the bright galaxies are dominated by one explanation or represent several different routes to early luminosity. The environmental context matters as well. The first galaxies did not form uniformly across space. Rare regions with unusually high initial density could collapse early and build halos faster than average. A deep Webb field that happens to intersect one such region may therefore contain more bright galaxies than a simple cosmic average would predict. This phenomenon, known as cosmic variance, becomes important when surveys cover small areas of sky. Expanding the surveyed area helps determine whether an apparent excess represents the universe as a whole or an especially productive region. Even with that uncertainty, the growing number of bright high redshift systems has altered the tone of the problem. Before Webb, the cosmic dawn was often pictured observationally as a realm dominated by objects just beyond reach, faint systems slowly assembling into recognizable galaxies. Webb is revealing that at least some parts of this era are already intensely luminous. Star formation can become vigorous quickly. Gas can organize into productive stellar systems while the universe is still extremely young. The first generations of galaxies may therefore have contributed more strongly to ultraviolet radiation, chemical enrichment, and reionization than conservative models once suggested. Their brightness is not merely an observational convenience that makes them easier to find. It is evidence that the machinery of galaxy formation can accelerate rapidly under early cosmic conditions. The deeper consequence is that the timeline of structure formation may remain broadly correct, while the pace of visible evolution within that timeline needs revision. Gravity still builds the halos. Expansion still sets the cosmic clock. The Big Bang framework remains intact. What Webb is changing is the expected efficiency of what happens inside those halos once gas begins to collect. A universe thought to be only beginning to light up may already contain regions where stellar production is intense, repeated, and capable of making galaxies visible across nearly the entire observable cosmos. The excess brightness therefore does not close the argument. It makes the next question harder, because if early galaxies could become luminous this quickly, then some of them may also have been able to build substantial stellar mass, organize structure, and even mature populations far sooner than expected. The first billion years of cosmic history were once expected to look unfinished in almost every visible sense. Galaxies could exist, stars could form, and dark matter halos could merge. But there seemed to be a natural limit on how much organization anyone's system could achieve before the universe had simply run out of time. Webb has complicated that picture. Some early galaxies are not merely bright. They appear to have accumulated substantial stellar populations, developed dense central regions, and in a few cases entered phases in which star formation has already weakened dramatically or stopped. That last condition is especially revealing. A galaxy that is actively forming stars can be young in a straightforward way. Gas is arriving, clouds are collapsing, and massive stars are continually replenishing the ultraviolet light. A quiescent galaxy is different. It carries evidence of an earlier period of growth that has already ended or slowed. For such a system to exist in the young universe, the entire sequence has to be compressed. Gas must collect. Stars must form rapidly, the stellar population must build enough mass to become detectable, and then some mechanism must suppress the process, all before much cosmic time has passed. Webb has now found examples that make this compressed history difficult to ignore. One spectroscopically confirmed massive quiescent system is observed roughly 1.2 billion years after the Big Bang. Yet its stars indicate that much of its growth occurred earlier still. Another much smaller quenched system has been identified when the universe was only about 700 million years old, showing that the shutdown of star formation was not restricted only to later, mature cosmic environments. These objects do not imply that all early galaxies evolved rapidly, or that the young universe was already filled with systems resembling modern ellipticals. They reveal something subtler. The range of possible evolutionary states had widened far earlier than expected. Some galaxies could still be primitive and vigorously growing, while others had already raced through a major phase of stellar assembly and begun to slow down. The existence of that diversity changes the problem from simple growth into timing. To understand why, it helps to separate the mass of a galaxy from its brightness. A short burst of star formation can make a relatively modest galaxy extraordinarily luminous, but building a large stellar mass requires converting a substantial reservoir of gas into stars over time. The process is constrained by the supply of baryonic matter, by the depth of the dark matter halo, by how efficiently gas can cool, and by the feedback produced as stars form. Massive young stars heat their surroundings. Supernovae can accelerate gas outward. Radiation can disrupt dense clouds before they finish collapsing. These effects normally act as brakes. If an early galaxy, nevertheless, builds a large stellar population quickly, either the fuel supply is exceptionally strong, the conversion of gas into stars is unusually efficient, the feedback is less effective at removing material, or the system passes through repeated episodes of intense growth faster than simple models anticipated. The young universe may offer conditions in which several of those factors occur together. Gas fractions are high. Matter is denser on average than at later epochs. Galaxies collide and merge frequently. Streams of gas can feed growing halos, while compact regions reach very high densities. Under these circumstances, star formation may proceed in violent but relatively brief episodes, rapidly increasing stellar mass before feedback reorganizes the system. That creates an evolutionary rhythm unlike the slow, extended growth often associated with large nearby galaxies. A young galaxy may spend a short interval consuming or expelling much of its available cold gas, then enter a quieter stage while the surrounding halo continues to evolve. The crucial question is what stops the stars from forming. Quenching, the suppression of star formation, has several possible causes, and none has yet emerged as a universal explanation for the earlier systems. Stellar feedback may heat or expel gas. A rapidly growing central black hole may release enough energy to disturb the gas supply. A merger may trigger an intense starburst that consumes fuel quickly and then leaves the galaxy depleted. Gas entering a sufficiently massive halo may be shock-heated and prevented from cooling efficiently. The structure of the galaxy itself can also matter, because a dense central concentration may alter the stability of the remaining gas. In the early universe, these mechanisms could overlap. And Webb is observing systems at precisely the period when their relative importance remains uncertain. A galaxy that appears quiescent is therefore not only evidence that star formation stopped, it is evidence that something capable of stopping it was already operating. This makes early quiescent galaxies unusually useful tests of formation models. Their stars preserve a rough memory of when the main growth episode occurred. Spectra can reveal breaks and absorption features associated with stellar populations that are no longer dominated by the youngest massive stars. From those features, models can estimate how long ago star formation peaked and how quickly it declined. The reconstruction is not exact. Stellar ages, dust, chemical composition, and star formation history can imitate one another in parts of a spectrum, and even Webb cannot remove every degeneracy. But spectroscopy greatly narrows the possibilities compared with broadband imaging alone. When the spectrum indicates both a substantial stellar population and little evidence for ongoing star formation, the implied history becomes demanding. The galaxy must have started building earlier than the moment at which it is observed. That pushes the onset of its growth deeper into the cosmic dawn. This same logic applies to massive galaxies that are still forming stars. Their observed stellar mass is a cumulative record. If a galaxy already contains a large amount of mass in stars when the universe is less than 1 billion years old, then the average rate at which those stars were assembled must have been high, unless the growth began at an extraordinarily early epoch. Either way, the available interval becomes short. This is why early massive galaxies generated so much discussion after Webb began returning data. Some first estimates were so extreme that they appeared difficult to reconcile with the amount of matter expected inside available dark matter halos. Improved spectroscopy and more careful treatment of emission lines, dust, and black hole light reduced several of those masses, removing the most dramatic conflicts. Yet the broader phenomenon survived the revisions. Webb still finds galaxies whose histories require rapid assembly, and independent studies increasingly suggest that the most efficient early systems may turn available gas into stars at rates higher than comparable, massive galaxies at later times. The issue has therefore become one of distribution rather than impossibility. Cosmology does not need every galaxy to follow an average path. Rare density peaks can collapse early. Unusually well-supplied halos can grow faster. Mergers can accelerate assembly. What matters is whether the observed number of fast-growing systems can be produced naturally within the available population of halos. If such galaxies are common, then models must allow efficient growth to occur under a wider range of early conditions. If they are rare, they may represent the extreme tail of an otherwise familiar process. Larger surveys are beginning to distinguish between those possibilities. The consequences extend beyond galaxy mass. Rapid stellar growth means rapid chemical enrichment, because massive stars begin producing and dispersing heavier elements almost immediately. It also means stronger ultraviolet radiation, more supernova, faster dust production, and potentially more rapid feeding of central black holes. A galaxy that forms most of its stars in a compressed episode can transform both itself and the space around it before later generations of galaxies have even begun to settle into stable forms. Early maturity therefore does not mean that these systems are modern galaxies appearing prematurely. Their environments, stellar populations, gas fractions, and merger rates remain distinctly ancient. The surprise is that some processes associated with later evolutionary stages can already be present. A compact galaxy may have completed a major star-forming episode while neighboring systems are still assembling. A dense core may emerge before a large disk has settled. A central black hole may become dynamically important while the surrounding stellar body remains small. Cosmic evolution is not a single synchronized ladder. Webb is revealing overlapping pathways running at very different speeds. That realization places new constraint on any model of the first billion years. It is no longer enough to reproduce when galaxies first appear or how bright they become. A successful model must also produce the observed spread in their history's systems still experiencing their first major bursts. Systems rapidly accumulating mass, and rare galaxies that have already crossed into temporary or sustained quiescence. The clock itself has not changed. The universe is still as young as the redshifts indicate. What has changed is the amount of evolution that nature appears capable of fitting inside that clock, and the next question is whether such accelerated growth also had enough time to create recognizable internal structure, rather than merely large collections of stars. The idea that the earliest galaxies should look chaotic has always been partly intuitive. If a system forms quickly, accretes gas from several directions, merges with smaller neighbors, and is repeatedly disrupted by stellar feedback, then an orderly internal structure seems difficult to maintain. The first galaxies were therefore often imagined as irregular collections of young stars and gas, still too unsettled to develop the organized features familiar in later cosmic epochs. Webb is showing that this expectation was too simple. Some galaxies less than 1 billion years after the Big Bang already display internal patterns that suggest disks, dense central regions, and distinct zones of star formation. These systems are not necessarily calm or mature in the modern sense. Their structures may be short-lived, unstable, and constantly rebuilt. Yet the fact that such organization appears at all places a new constraint on how quickly matter can move from collapse into architecture. One particularly revealing example is a galaxy observed roughly 900 million years after the Big Bang, in which Webb resolved at least 15 separate star-forming regions across a larger stellar structure. The significance lies not only in the number of clumps. The distribution suggests that star formation is occurring within an organized galaxy, rather than inside a completely unstructured cloud. A central concentration is also present, indicating that the inner part of the system may already be developing differently from the outer disk. This is important because many galaxies in the modern universe show evidence of inside-out growth, with dense central components forming early, while disks continue accumulating material around them. Finding hints of that pattern so far back in time suggests that at least some mechanisms associated with later galaxy evolution begin operating much sooner than expected. A disk itself is a demanding structure. Gas entering a dark matter halo does not simply settle into a thin rotating plane automatically. It carries angular momentum, the tendency of moving matter to continue rotating, and that angular momentum can be redistributed by collisions, gravitational torques, mergers, and interactions with surrounding gas. For an extended disk to emerge, enough material must acquire a reasonably coherent direction of rotation. The system must then preserve that organization despite continuing inflow and disturbance. In the early universe, where mergers are frequent and gas fractions are high, this can be difficult. Yet observations increasingly suggest that rotation becomes established quickly in at least some galaxies. A young disk may be thicker, more turbulent, and more fragmented than the disks of many nearby spirals, but it can still possess ordered motion. This distinction matters. Turbulence does not necessarily erase structure. A galaxy can be dynamically violent while still rotating as a whole. Dense clumps can form within the disk, move inward, interact, and help build a central concentration. The galaxy may therefore look irregular in detail while remaining organized at a larger scale. Webb sensitivity and resolution in the infrared make these distinctions easier to detect. Earlier telescopes often saw the combined light of a distant galaxy, without resolving its internal components clearly. Webb can separate compact regions of enhanced star formation, measure color differences across a galaxy, and reveal whether a bright central region is physically distinct from the surrounding disk. Spectroscopy can add information about gas motion, allowing astronomers to test whether different parts of a system share a coherent rotational pattern or are moving independently after a merger. The emerging picture is not one in which early galaxies instantly resemble the Milky Way. It is one in which the basic ingredients of later structural evolution appear surprisingly early. Dense cores can begin forming. Rotating disks can exist. Star formation can become concentrated into discrete clumps. The important question then becomes how these features arise so quickly. Gas supply is one possible answer. Early galaxies are embedded in an environment where fresh material can flow rapidly into growing halos. If that gas arrives with consistent angular momentum over a sufficient period, it can build a rotating structure even while the system remains turbulent. At the same time, the gas-rich disk can become gravitationally unstable. Regions with slightly greater density collapse into massive star-forming clumps, producing the separated knots of light that Webb can resolve. These clumps may not remain where they form. Through gravitational interactions with the rest of the disk, they can lose angular momentum and drift inward over time. Repeated inward migration can add material to the center and help construct a compact core. This offers one route to inside-out evolution that does not require a galaxy to pass through a long, quiet phase first. The same turbulent conditions that make an early disk unstable may actually accelerate the creation of internal structure. Mergers provide another route. Two or more small galaxies can combine, rearranging stars and gas while driving material toward the center. A merger may trigger a burst of star formation, strengthen a central concentration, and eventually settle into a new rotating configuration if enough gas remains. In this sense, order and disturbance are not opposites separated by long intervals. A disturbed system can generate structure precisely because gravitational interactions redistribute matter so efficiently. The early universe may therefore move through cycles of organization and disruption, rather than a simple progression from chaos to stability. That possibility changes how morphology, the observed shape of a galaxy, should be interpreted at high redshift. A disk seen at one moment does not prove that the disk has survived for hundreds of millions of years. A central core does not necessarily mean that the galaxy followed the same path as a nearby spiral or elliptical. These features are snapshots of systems evolving rapidly. Their value comes from showing that the physics required to create them is already active. The presence of many star-forming regions is especially useful because it reveals how stellar growth is distributed. If most star formation occurred only in the center, then a galaxy might build from the inside with little activity at large radius. If numerous clumps are scattered through a disk, then growth is happening across a wider area. Over time, the central region may become denser, while the disk continues to expand as new gas arrives. This provides a natural way for size and structure to change together. It may also help explain why some later galaxies contain old central stellar populations surrounded by younger material. The first stages of that separation could begin within the first billion years. Yet rapid structure creates another tension. Internal organization requires time not only for gas to settle, but for orbital motion to redistribute matter. A galaxy observed 900 million years after the Big Bang has had more time than a system like Z14, but not much by the standards of galactic evolution. If a dense core is already present, then the processes that built it must have begun significantly earlier. If several distinct star-forming regions have developed across a disk, then the disk itself must already have acquired enough coherence to support them. Once again, the visible object pushes its history backward. The galaxy is evidence not only of what exists at the time of observation, but of earlier stages that had to occur before that structure became detectable. Models must reproduce that sequence. They must allow dark matter halos to grow, gas to accrete, angular momentum to organize the inflow, instabilities to create clumps, and central concentrations to emerge, all while strong feedback and frequent interactions continue to disturb the system. The challenge is not necessarily that any single process is unknown. Most of the relevant mechanisms are already familiar. The difficulty lies in their speed, efficiency, and interaction under early cosmic conditions. This is similar to the problem created by unexpectedly bright galaxies. The broad physical framework remains intact, but the parameters controlling the rate of visible evolution may need adjustment. High gas fractions may make disks more unstable. Dense environments may shorten dynamical times. Frequent inflows may rebuild rotating structures after disruption. Clumps may migrate inward faster. Feedback may regulate star formation without destroying the entire disk. Different combinations can produce galaxies that are simultaneously young, turbulent, and structurally complex. Webb is beginning to distinguish among the possibilities by resolving larger samples across a range of redshifts. If organized disks become increasingly rare at earlier times, that would reveal a transition in how galaxies acquire stable rotation. If central concentrations appear only above certain masses, that would connect structure to halo growth and gas supply. If clumpy star formation is nearly universal in the earliest disks, then instability may be a defining feature of early assembly rather than an exception. Each pattern turns morphology into a clock of sorts, not one that gives an exact age, but one that reveals which physical stages have already occurred. The deepest implication is that cosmic youth does not require structural simplicity. Galaxies can be unsettled and organized at the same time. Their disks can rotate while remaining turbulent. Their cores can grow while mergers continue. Their star-forming regions can be distinct even while the entire system is changing quickly. The early universe therefore appears less like a long wait for recognizable galaxies, and more like a period in which recognizable features emerge, disappear, and reappear under intense conditions. That makes the next set of Webb discoveries especially difficult to interpret, because not every compact red source fits neatly into the categories of disk, core, or star-forming clump. Some are smaller, redder, and stranger, and their light may be revealing a different engine of early cosmic growth altogether. The little red dots appeared in Webb observations not as enormous galaxies or obvious quasars, but as compact sources whose simplicity in an image concealed a much more difficult physical problem. They are small, red, and often unresolved or only barely resolved even with Webb's sharp infrared vision. Yet their spectra and brightness suggest that some of them contain far more energetic activity than their appearance would imply. Before Webb, this population was largely hidden because earlier observatories lacked the same combination of sensitivity, wavelength coverage, and spatial resolution in the infrared. Once Webb began surveying the early universe, these objects appeared often enough to look less like isolated curiosities and more like a distinct class of high redshift sources. Their importance comes from what their light may be revealing. A compact red object can, in principle, be explained in several ways. It might be a small galaxy filled with stars whose light has been reddened by dust. It might contain an unusually dense stellar population. It might be dominated by an active galactic nucleus, where a central black hole is accreting gas and releasing enormous amounts of radiation from a region much smaller than the galaxy around it. Or it might combine several of these effects at once. The difficulty is that some little red dots do not fit comfortably into the simplest versions of any one explanation. Their colours are red in ways that can suggest dust or older stars, yet other parts of their spectra imply intense ionizing radiation. Some are extremely compact, concentrating substantial luminosity into a very small area. Several show broad emission lines, one of the classic signs that gas is moving at very high velocities near an accreting black hole. In nearby active galaxies, broad lines often arise from gas orbiting close to a supermassive black hole, where gravity accelerates material to thousands of kilometers per second. Finding similar signatures in small red sources from the early universe immediately raises the possibility that black hole growth was already widespread. That possibility changes the interpretation of their light. If stars alone are assumed to produce most of the emission, then some little red dots can appear to contain remarkably dense and massive stellar populations packed into very small volumes. In some cases, that would make them difficult to reconcile with ordinary expectations for young galaxies. If an accreting black hole contributes a significant fraction of the light, the inferred stellar mass can fall, because part of the luminosity no longer needs to be explained by stars. The same object then moves from being an improbably dense stellar system to being evidence for an unexpectedly active black hole. Neither interpretation is trivial. A massive compact galaxy forming so early places pressure on models of stellar assembly. A rapidly growing black hole places pressure on models of black hole seeding and growth. The little red dots therefore sit at an intersection between two of Webb's broader surprises. Early galaxies seem capable of building stars rapidly, while early black holes seem capable of becoming influential far sooner than expected. The red colour itself adds another layer. Dust is one natural way to redden light because small dust grains absorb shorter wavelengths more efficiently than longer ones. A heavily obscured active nucleus can therefore look red even while producing tremendous intrinsic luminosity. Yet dust requires heavy elements, and heavy elements require earlier generations of stars. In the first billion years, enough time has passed for dust to form, especially around supernovae and evolved stars. But the amount and distribution of that dust are part of the question. If some little red dots are deeply obscured black holes, then the system surrounding them must already have undergone enough chemical enrichment to produce the material hiding the central source. The black hole would not be evolving in a pristine environment. It would be embedded within a galaxy that had already experienced significant stellar processing. Other little red dots show a different problem. Their spectra can display both a red optical component and a much bluer ultraviolet component, as though different physical sources contribute at different wavelengths. A compact accreting black hole may dominate one region of the spectrum while young stars contribute another. Scattered nuclear light may also complicate the appearance. This mixed character makes simple classification difficult. Webb is effectively observing systems during a period when the familiar distinction between galaxy and active nucleus may not yet be clean in the modern universe. A large galaxy can contain a central black hole that represents only a tiny fraction of the total stellar mass, and astronomers can often separate the extended host from the compact nucleus. In the early universe, the host may still be small while the black hole is growing rapidly. The relative importance of the nucleus can therefore be much greater. A source that appears as a tiny point of light may represent a galaxy in which the central black hole is already competing with the stars for control of the system's observed luminosity. This possibility helps explain why little red dots are especially common across a particular period of early cosmic history rather than throughout all epochs with the same frequency. Webb observations suggest that they become conspicuous hundreds of millions of years after the Big Bang and remain common through portions of the first few billion years before becoming less dominant later. If many are connected with black hole growth, the distribution may be showing a phase in which compact galaxies and rapidly feeding black holes frequently coexist. The early universe supplies abundant gas. Galaxies are gas-rich. Mergers and gravitational disturbances are common. Dense central regions can funnel material inward. These conditions can feed black holes efficiently, at least for limited periods. An accreting black hole does not consume matter directly from a cold reservoir without consequence. Gas falling toward it forms a disk, heats through friction and compression, and releases radiation before crossing the event horizon. That radiation can become so intense that it pushes against surrounding material. At sufficiently high accretion rates, radiation pressure can limit how quickly additional gas falls inward. This creates the familiar growth problem for early black holes. If the seed begins with the mass of an ordinary stellar remnant, repeated periods of efficient accretion are required to reach millions or tens of millions of solar masses within the first billion years. Interruptions make the timing harder. Larger initial seeds make it easier. The little red dots may therefore be more than a newly recognized category of compact object. They may be observational markers of the period when early black hole seeds were rapidly gaining mass. Their abundance could eventually help determine which seeding pathways were common. If most contain modest black holes growing efficiently, then smaller seeds may have had time to catch up. If many host black holes already unusually massive relative to their galaxies, then heavy seed scenarios become more attractive. Those scenarios include the direct collapse of massive gas clouds under conditions that suppress ordinary fragmentation into stars, instead of beginning with a black hole only several or tens of times the mass of the Sun. The process could create a seed thousands or perhaps far more times as massive, shortening the path to a later supermassive black hole. The observations have not settled which pathway dominates. That uncertainty is one reason little red dots remain scientifically valuable. They offer a population rather than a single spectacular example, and populations can reveal patterns that isolated records cannot. Their number density, redshift distribution, spectra, variability, sizes, and relationship to surrounding galaxies can all test competing models. If their light varies strongly over time, that would support compact accretion as a major energy source. If deeper observations reveal extended stellar hosts, astronomers can estimate how the black hole and galaxy masses compare. If X-ray or other high-energy signatures are unusually weak, models must explain how accreting black holes can remain hidden at those wavelengths while remaining bright in the infrared. Heavy obscuration, unusual accretion geometry, or dense surrounding gas may all play a role. There is also a possibility that the little red dot category contains more than one physical type of object. Similar colors can emerge from different mechanisms. Some may be dominated by active black holes, others by exceptionally compact stellar systems, and still others by mixtures that change as the galaxies evolve. Webb may have grouped them observationally before nature has provided a single physical explanation. That would not reduce their importance. It would mean that the early universe produced several kinds of compact luminous systems that earlier telescopes could not separate. The most revealing feature of the little red dots is therefore not simply their redness. It is the mismatch between their small visible size and the amount of activity their light seems to contain. They suggest that processes once associated with larger, more developed galaxies can become concentrated into remarkably compact systems during the first chapters of cosmic history. If black holes are responsible for much of that emission, then their growth was not a rare afterthought, occurring only after galaxies had matured. It may have been woven into galaxy assembly from the beginning, sometimes strongly enough that the central black hole becomes one of the defining features of the young system. That possibility leads directly to a harder timing problem. A hidden population of rapidly accreting black holes can explain some of Webb's puzzling compact sources, but it also means that the universe had already produced black holes large enough to influence their hosts at ages when conventional stellar seeds had very little time to grow. A black hole with a mass of several million suns is not difficult to explain in the modern universe, where billions of years have passed and galaxies have experienced countless episodes of star formation, mergers, and gas inflow. The same object becomes far more demanding when it's observed only a few 100 million years after the Big Bang. Webb is now finding evidence that black holes had already become substantial components of some early galaxies during exactly that narrow interval. In several systems, the inferred masses reach millions or even tens of millions of solar masses, while the surrounding galaxies remain small by later cosmic standards. The puzzle is therefore not whether gravity allows such black holes to exist. It does. The puzzle is whether enough time exists to build them through the ordinary sequence expected for stellar remnants. The conventional path begins with a massive star. After exhausting its nuclear fuel, the star collapses and may leave behind a black hole, with a mass perhaps several times or several tens of times that of the Sun. If this remnant finds itself inside a dense young galaxy, gas can begin falling toward it. Matter rarely plunges directly into the event horizon. Instead, angular momentum causes the gas to form an accretion disk, where friction and compression heat the material until it radiates enormous amounts of energy. Some mass is eventually added to the black hole, allowing it to grow. The difficulty is that accretion creates its own resistance. The brighter the disk becomes, the more radiation pushes outward against the surrounding gas. At a characteristic level known as the Eddington limit, outward radiation pressure begins competing strongly with the inward pull of gravity. A black hole can sometimes exceed this level, especially under complex conditions. but sustained growth at very high rates is difficult. If a small stellar remnant grows near the Eddington rate, its mass can increase exponentially, doubling repeatedly over cosmic time. That sounds fast until the starting point and available interval are considered together. To turn a black hole of only several tens of solar masses into one containing millions or tens of millions of solar masses requires many successive growth cycles. The black hole must also remain well supplied with gas throughout much of that period. Any interruption matters. Stellar explosions can remove gas from the nucleus. Radiation from the accretion disk can heat nearby material and reduce inflow. Galaxy mergers can both feed and disturb the central region. The black hole may spend long intervals growing slowly between brief active phases. By the time Webb observes some early systems, however, the required mass is already present. This means that either growth began extremely early, proceeded with unusual efficiency, started from a much larger seed, or followed some combination of these routes. The seed problem is therefore central to understanding early black holes. A stellar remnant is often called a light seed because its initial mass is small compared with the supermassive object it may eventually become. A heavy seed begins much farther along. One possible heavy seed pathway involves the direct collapse of a large gas cloud. Under the right conditions, gas flowing into an early dark matter halo might avoid fragmenting efficiently into ordinary stars. If cooling and chemistry remain within a narrow range, the cloud can continue collapsing toward the center while retaining enough mass to form an extremely massive star or another unstable intermediate object. That structure may then collapse into a black hole containing thousands, tens of thousands, or potentially more solar masses from the beginning. The precise outcomes remain uncertain, but the advantage is straightforward. A black hole starting with a large seed needs fewer rounds of exponential growth to reach the masses Webb is beginning to infer. Direct collapse is not expected to happen everywhere. The conditions required may be rare. Nearby sources of ultraviolet radiation can alter the chemistry of the gas and suppress the formation of molecular hydrogen, which otherwise helps clouds cool and fragment. Rapid inflow may be necessary. The halo must reach sufficient mass while remaining chemically primitive enough that heavy elements and dust do not cause the gas to break into smaller star-forming pieces. These requirements make heavy seeds difficult to produce. But rarity is not necessarily a problem if the earliest massive black holes themselves occupy unusual environments. Another possible route begins with dense clusters of stars. In an extremely crowded young cluster, repeated stellar collisions and mergers may create a very massive star that later collapses into a black hole larger than a normal stellar remnant. Black holes inside clusters may also merge with one another. This pathway produces seeds between the lightest stellar remnants and the most extreme direct collapse scenarios. The young universe could therefore have generated black holes through several channels, rather than one universal mechanism. Webb's observations may eventually reveal which route was most important by measuring how frequently early black holes appear and how their masses compare with those of their host galaxies. Growth after seeding remains equally important. Even a heavy seed must continue gaining mass if it is to become a tens of millions solar mass object within the first billion years. Gas-rich early galaxies offer favorable conditions. Their central regions can be dense, and repeated mergers or instabilities can drive gas inward. Large clumps forming in turbulent disks may migrate toward the center and deliver additional material. A black hole embedded in such an environment could experience episodes of rapid feeding. Some theoretical models allow super-Eddington accretion, in which matter reaches the black hole faster than the classical radiation limit would suggest. This does not necessarily violate the physics behind the limit because the geometry of the flow can change the way radiation escapes. In very dense accretion disks, Some radiation can become trapped and carried inward with the gas rather than pushing all of the surrounding material away. Outflows may escape along certain directions while inflow continues through others. Under those conditions, a black hole can temporarily gain mass faster than a simple spherical model permits. The key word is temporarily. Sustaining such growth over long intervals remains difficult, and observations must determine whether repeated rapid episodes were common enough to solve the early mass problem. Black hole mergers provide another contribution, but they are unlikely to remove the need for efficient gas accretion by themselves. When galaxies merge, the black holes they contain may eventually sink toward the common center through interactions with stars and gas. If they form a close pair and finally merge, their masses combine, minus a small amount carried away as gravitational radiation. Repeated mergers can accelerate growth, especially in the crowded early universe. Yet merging also takes time, and the process of bringing two black holes together can stall under some conditions. The earliest massive objects, therefore, probably reflect a combination of seeding, accretion, and mergers rather than a single uninterrupted pathway. Webb adds a new dimension because it can examine the relationship between the black hole and the surrounding galaxy at stages that were previously inaccessible. In nearby galaxies, the mass of the central supermassive black hole is often only a small fraction of the stellar mass of the host. The two appear to have evolved together over long periods, connected through gas supply and feedback. Some early Webb systems look very different. Their black holes may represent an unusually large fraction of the total mass contained in stars. If those estimates hold, then the familiar relationship between galaxy and black hole has not yet been established. The black hole may be growing first, while the stellar component catches up later. That possibility is significant because it reverses a common intuitive sequence. Instead of a mature galaxy gradually feeding a central black hole until it becomes supermassive, a large seed may appear inside a young halo and become one of the dominant engines shaping the galaxy from an early stage. Radiation and outflows from the growing black hole could then heat gas, regulate star formation, or drive material away from the center. At other times, the same gravitational environment that feeds the black hole may also fuel an intense stellar population around it. Galaxy growth and black hole growth would remain connected, but neither would simply wait for the other to finish. This is why the earliest black holes carry implications beyond their own mass. They test the chronology of galaxy assembly itself. If light seeds dominate, then early galaxies must provide almost continuous feeding or repeated periods of extremely rapid accretion. If heavy seeds dominate, then the universe must produce direct collapse environments, often enough to account for the observed population. If both channels operate, then Webb may be observing a mixture whose different origins can eventually be separated through black hole mass, host mass, chemical state, and redshift. The discovery of more early active black holes will make that distinction increasingly testable. At present, the evidence does not require a new law of gravity or the abandonment of standard cosmology. It requires a more complete account of how quickly compact objects can form inside the environments created by that cosmology. The universe provides the time available. Webb is now showing how much growth nature managed to fit inside it. That is where the pressure lies. A black hole containing millions of solar masses after billions of years is an expected consequence of long evolution. The same mass after only a small fraction of the first billion years becomes a record of unusually early decisions made by gas, gravity, radiation, and collapse. And once such a black hole is found in a galaxy that is still small, the question is no longer only how the black hole became so large, but whether the black hole may have begun shaping the galaxy before the galaxy had fully formed around it. Able 2744 QSO1 is difficult to interpret using the familiar picture in which a galaxy forms first, and its central black hole grows gradually afterward. Webb observes this system from roughly 700 million years after the Big Bang, at a time when both galaxies and black holes should still be in relatively early stages of development. Yet the central black hole is already inferred to contain around 50 million times the mass of the Sun, an extraordinary value when compared with the comparatively modest stellar system surrounding it. The unusual feature is not simply the absolute mass of the black hole. It is the ratio between the black hole and its host. In many galaxies in the later universe, a central supermassive black hole represents only a small fraction of the stellar mass of the entire galaxy. Observable 2744 QSO1 appears to sit much farther from that familiar balance. Its black hole may contain a remarkably large share of the mass associated with the visible system, raising the possibility that black hole growth has moved ahead of galaxy growth rather than merely following it. That possibility changes the sequence normally imagined for galactic evolution. A large galaxy does not necessarily have to assemble most of its stars before it can support a massive central black hole. Under some early cosmic conditions, the black hole seed may appear quickly, begin accreting efficiently, and become one of the dominant structures in the system while the surrounding galaxy is still building itself. The object lies behind the massive galaxy cluster Able 2744. Whose gravity bends and magnifies more distant light through gravitational lensing. That natural magnification helps Webb examine sources that would otherwise be more difficult to study, allowing astronomers to probe the physical character of the quasar and its host at an epoch where such measurements are normally challenging. What emerges is not a fully developed modern galaxy containing an unusually active nucleus. It is something closer to a young system in which the nucleus may already be disproportionately important. A quasar is produced when a black hole accretes material rapidly enough for the surrounding disk to become intensely luminous. Gas spiraling inward releases gravitational energy as heat and radiation before some of it reaches the event horizon. The resulting light can outshine large portions of the host galaxy. This creates an observational complication because the brighter the black hole becomes, the harder it can be to measure the stars around it. Webb's infrared sensitivity helps separate components of the system, but any estimate of the host still depends on interpreting light from an object where stars, gas, dust, and the active nucleus overlap. Even with those uncertainties, the central black hole remains strikingly massive for such an early time. If the estimate is broadly correct, then the growth history must begin significantly earlier than the moment Webb observes. A 50 million solar mass black hole cannot appear instantaneously. Either it begins from an already massive seed, grows extremely rapidly, or both. The host galaxy must also begin assembling stars before the observed epoch, but the apparent mass balance suggests that its stellar growth has not kept pace with the central object. This creates a version of the black hole seed problem that is more specific than simply asking how early supermassive black holes formed. It asks how their growth related to the growth of the galaxies around them. One possibility is that a massive seed forms through direct collapse. In this scenario, a large cloud of gas avoids fragmenting extensively into ordinary stars and instead undergoes a much more concentrated collapse. The resulting seed can begin with thousands or perhaps far more solar masses, rather than the much smaller mass of a normal stellar remnant. If that seed forms early enough and receives a strong gas supply, the path to tens of millions of solar masses becomes considerably shorter. The surrounding galaxy does not need to be massive at the beginning. The dark matter halo and gas reservoir only need to create conditions favorable to central collapse and continued feeding. The black hole can then grow while the stellar component develops around it. This is one reason Able 2744 QSO1 has become important in discussions of heavy seed models. A system with an unusually high black hole to stellar mass ratio resembles what might be expected during a phase when the central seed has already become large, but the host has not yet caught up. That does not prove direct collapse occurred. Other pathways may produce similar outcomes. A lighter seed could grow through sustained or repeated episodes of very rapid accretion, especially if the early nucleus remains continuously supplied with dense gas. Mergers between smaller black holes could add mass as well. The observational question is whether the ratio seen in the system is temporary, representing a short stage in coevolution, or whether it reflects a distinct formation pathway common among the first black holes. If it is temporary, the galaxy may eventually grow around the black hole until the relationship begins to resemble those seen at later times. Fresh gas can continue entering the halo. Star formation can increase the stellar mass. Mergers can add new stars and gas from neighboring systems. Over hundreds of millions of years, the galaxy may effectively catch up. The black hole itself may also slow once its radiation and outflows become strong enough to regulate the supply reaching the center. In this picture, the unusual mass ratio is not a permanent anomaly, but an early snapshot of two connected growth processes moving at different speeds. The alternative is more consequential. If many early systems show similarly overmassive black holes, then the standard intuition of galaxies nurturing black holes may need to be reversed for at least part of the population. Massive black hole seeds could become central organizing structures from the beginning, influencing how gas cools, where stars form, and how matter is distributed inside the growing galaxy. Energy released by accretion can heat surrounding gas and drive outflows away from the nucleus. Those outflows may suppress star formation by removing or heating fuel. Yet under other conditions they may compress nearby gas and alter where new stars appear. The effect is therefore not simply destructive. A growing black hole can participate in the regulation of its host while both are still young. This would mean that black hole feedback, often discussed as an important ingredient in the later evolution of massive galaxies, may already be active during the first billion years. Able 2744 QSO1 also illustrates why the phrase black hole before its galaxy needs careful interpretation. The system clearly contains a galaxy. Stars and gas are already present. The claim is not that a black hole existed in complete isolation and later manufactured a galaxy around itself. The more precise idea is that the black hole may have reached a substantial fraction of its eventual mass before the surrounding stellar system had reached a comparable stage of development. In relative terms, the black hole could be ahead. That distinction keeps the interpretation anchored to what Webb actually measures. The telescope sees a young host and an unusually massive central object. From that imbalance comes the possibility of an inverted growth sequence. The significance grows if similar systems appear elsewhere. One object can always represent an extreme environment. A population begins to define a pattern. Webb's little red dots may already be hinting that compact, rapidly accreting black holes are not rare during some early epochs. If detailed spectroscopy shows that many of those sources also contain black holes unusually massive relative to their hosts, then Able 2744 QSO1 would no longer look like an isolated exception. It would become part of a broader phase in which black hole growth frequently outran stellar assembly. That would provide an important clue to the origin of the billion solar mass quasars known from somewhat later cosmic times. Those later quasars require substantial seeds and sustained growth somewhere in their history. Systems like this may represent earlier stages of the same evolutionary chain, caught before the surrounding galaxy becomes massive enough to hide how unusual the initial ratio once was. The deeper issue is therefore not which object technically formed first. Dark matter, gas, stars, and black holes evolve together in a connected environment The important question is which component gains mass fastest during the earlier stages. In Able 2744 QS01, Webb appears to be showing a system where the central black hole has moved far ahead. If that interpretation survives better measurements, then the earliest galaxies may not simply be structures that eventually produce massive black holes at their centers. In some cases, they may be structures whose later growth unfolds in the presence of a black hole that became enormous almost from the beginning. JWST Z13-1 is valuable because its light carries evidence not only about a young galaxy, but about the condition of the universe surrounding it. When this system is observed, the cosmos is still within the broad era of reionization, a period when much of the hydrogen between galaxies is changing from a neutral state into an ionized one. That transition is easy to describe in a single sentence and much harder to reconstruct in detail. Neutral hydrogen is not opaque to every kind of light, but it strongly absorbs ultraviolet radiation at particular wavelengths, especially the energetic photons capable of removing electrons from hydrogen atoms in the young universe before large regions became ionized. This created something like a widespread cosmic fog for ultraviolet light. The first luminous objects had to alter that environment before the universe could become as transparent to such radiation as it is at later times. Webb is now beginning to observe galaxies that may have participated directly in that transformation. The significance of JWST Z13-1 lies in the possibility that a galaxy appearing so early was already embedded within a region where neutral hydrogen had been cleared or ionized more strongly than expected. Its spectrum suggests that energetic radiation is escaping from the system and interacting with its surroundings, raising the possibility that ionized bubbles were forming around some galaxies surprisingly soon after the first sustained episodes of star formation began. Reionization does not happen because the universe suddenly switches from one state to another. It is gradual, uneven, and strongly dependent on where the first luminous sources appear. A young galaxy containing hot, massive stars produces large amounts of ultraviolet radiation. Some of those photons are absorbed inside the galaxy by gas and dust, but some may escape into intergalactic space. When an energetic photon encounters a neutral hydrogen atom, it can remove the electron, leaving behind an ionized proton if the galaxy produces enough such radiation, and if a large enough fraction escapes, an ionized region develops around it. Neighboring galaxies can contribute their own radiation, creating overlapping zones. Over time, many separate bubbles grow, connect, and eventually transform most of intergalactic hydrogen from neutral to ionized. The timing of this process matters because it links the internal physics of early galaxies to a change in the large-scale state of the universe. A galaxy that forms stars efficiently does not only increase its own brightness, it can alter the medium around it. A population of unusually luminous early galaxies could therefore have consequences far beyond the galaxies themselves. This is where Webb's earlier surprises begin to connect. If high redshift galaxies are brighter or more numerous than expected, then they may also contribute more ionizing radiation than older models assumed. If their stellar populations are metal-poor and weighted toward hot massive stars, they may produce particularly strong ultraviolet emission. If early galaxies contain less dust, a larger fraction of that radiation may escape. Each of these effects can accelerate reionization. The difficulty is that measuring the escape of ionizing radiation directly from such distant galaxies is extremely challenging. Much of the crucial ultraviolet light is absorbed before reaching the telescope. Astronomers therefore rely on indirect clues in spectra, the strength and shape of emission features, and the way radiation appears to have passed through the gas surrounding the source. JWST Z13-1 is important because it provides one of those clues at an exceptionally early time. The interpretation is not that the galaxy single-handedly cleared the universe around it. A single object cannot explain a transformation occurring across cosmic scales. The suggestion is narrower and more useful local regions of ionized hydrogen may have formed earlier than a smooth, average picture would imply. The first galaxies inhabit an uneven universe, so their influence should also be uneven. Dense regions form galaxies earlier. Groups of galaxies can develop close enough together for their combined ultraviolet output to become significant. Their ionized bubbles may therefore grow much faster than those around isolated systems. In other regions, neutral hydrogen may persist far longer. Reionization is thus expected to resemble a patchwork before it becomes nearly complete, with expanding transparent regions surrounded by still neutral space. Webb's deepest observations are beginning to probe this patchiness directly. A very high redshift galaxy can serve as both a source of radiation and a background beacon whose spectrum records material along the line of sight. Certain spectral features are suppressed when neutral hydrogen is abundant. Others become easier to observe if the galaxy lies inside an ionized bubble, large enough to prevent nearby neutral gas from absorbing the light immediately. The appearance of strong hydrogen emission from a galaxy at a time when the surrounding universe should still contain substantial neutral hydrogen can therefore imply that the local environment has already been altered. That is the kind of tension presented by JWST 13.1. Its light suggests that the conditions around at least some early galaxies may have been more transparent than expected for such a young cosmic age. If that interpretation is correct, then the ionizing process must have begun before the moment represented by the observation. Stars had to form, produce ultraviolet radiation, and maintain that radiation long enough for an ionized region to develop. Neighboring sources may have contributed as well, once again. The visible object points backward toward processes that began earlier than the telescope can directly see. The problem becomes one of efficiency. Astronomers need to know how many ionizing photons early galaxies produce, what fraction escapes, and how long the galaxies remain active. A bright galaxy with a very low escape fraction may contribute less to reionization than a fainter system whose radiation leaks more freely into intergalactic space. Small galaxies may therefore be crucial even if they are individually difficult to detect. Their greater numbers could allow them collectively to dominate the ionizing budget. Webb is beginning to reveal more of this faint population, but the accounting remains incomplete. The telescope is most sensitive to galaxies bright enough to cross its detection limits, while many smaller systems may remain below them. This creates an important distinction between the galaxies that are easiest to study and the galaxies that did most of the work. A rare bright galaxy can carve out a large ionized region, especially if it sits within an overdense environment, but the global transformation of the universe may depend on vast numbers of less luminous systems. Black holes may also contribute ionizing radiation, adding another connection to Webb's discoveries. Accreting black holes produce energetic spectra capable of ionizing gas over large distances. If compact active nuclei and little red dots are common in the early universe, their contribution to reionization may need to be reconsidered. Current evidence does not require black holes to dominate the process, and stars remain a natural primary source in many models. But Webb is making it possible to test whether early accreting black holes supplied a larger fraction of energetic radiation than previously assumed. The distinction may eventually be visible in the spectral signatures of the surrounding gas. Hard radiation from black hole accretion interacts with matter differently from the radiation field produced by stellar populations, and larger samples may reveal how frequently the two sources overlap. Reionization also feeds back into galaxy formation. Once intergalactic hydrogen becomes ionized, the gas is heated. Heating can make it more difficult for shallow gravitational wells to capture and retain material. The smallest galaxies may therefore experience reduced gas supply after their environments become strongly ionized. The same population responsible for transforming the intergalactic medium can gradually change the conditions for later low-mass galaxy formation. This makes reionization both a consequence of the first galaxies and an influence on what forms after them. Webb is examining that feedback near the point where it begins. The broader picture remains incomplete because a few extreme systems cannot establish the history of the entire universe. Astronomers need many galaxies across different redshifts and environments to determine how rapidly the neutral fraction declines with time and how large ionized regions become. They need spectroscopy to establish secure distances and identify the emission features that trace local conditions. They also need complementary measurements of the intergalactic medium from other observatories, because no single telescope can reconstruct every stage of reionization alone. Webb's contribution is to place the galaxies themselves into the center of the story. Instead of inferring the sources mainly from the later state of the universe, astronomers can now examine objects that were active while the transformation was still underway. This is why the apparent clearing around JD's GSZ 13.1 matters. It is not evidence that the cosmic fog had already vanished everywhere. It is evidence that the fog may have been punctured early, locally, and perhaps more efficiently than expected around certain galaxies. The young universe was not uniformly dark and then uniformly transparent. It was becoming transparent from the inside out, around the places where stars and possibly black holes were releasing enough energy to change the surrounding hydrogen. If Webb continues finding such systems at still earlier times, then the beginning of reionization may have to be pushed closer to the first episodes of galaxy formation, and that would sharpen the central question running through these observations, whether the early universe truly evolved faster than expected, or whether it only appears that way because the first models underestimated how productive its youngest galaxies could be. The claim that James Webb broke the Big Bang spread quickly because it compressed a complicated scientific discussion into a dramatic sentence. The real situation is far more precise. Webb has found galaxies that are brighter, more numerous, and in some cases more developed than many pre-launch models expected at very high redshift. Those results matter. They force astronomers to revisit assumptions about how efficiently gas formed stars, how quickly early galaxies assembled, and how much light young stellar populations could produce. But none of that is the same as disproving the Big Bang. The Big Bang is not a single prediction about when the first bright galaxies should appear. It is a broad framework describing an expanding universe that was once hotter and denser than it is now, a framework supported by several independent lines of evidence. The expansion itself is measured through the redshift of distant galaxies. The cosmic microwave background records radiation released when the universe became transparent. The abundances of light elements such as hydrogen and helium agree closely with calculations from an early hot phase. Webb does not erase those observations. In fact, the telescope relies on the same expanding universe framework when astronomers convert extreme redshifts into cosmic ages. The tension created by Webb lies farther downstream, in the detailed physics of how structure grows inside that expanding universe. Confusion became especially easy during the first wave of Webb discoveries, because many of the earliest record-breaking objects began as photometric candidates. Photometry measures how bright an object appears through a series of wavelength filters. At extreme redshift, a galaxy can show a distinctive pattern because neutral hydrogen absorbs much of the radiation shortward of a particular ultraviolet wavelength. Cosmic expansion shifts that break into the infrared. So astronomers can estimate redshift by determining between which filters the light suddenly weakens or disappears. The method is powerful because it allows large numbers of faint galaxies to be identified efficiently. it is also probabilistic. A photometric redshift is not the same as a direct measurement of how individual spectral features have shifted. Different physical conditions can sometimes imitate one another. A near a galaxy containing dust can appear unusually red. Strong emission lines can fall into one infrared filter and make an object look brighter there than expected. An older stellar population can produce a pronounced change in color. Detector noise becomes more important near the faintest limits. If only a few filters contain significant detections, several possible redshifts may fit the same measurements. For most objects, careful modeling can assign probabilities to those alternatives, but the most exciting candidate is not automatically the most secure one. This distinction became crucial when some early Webb sources were initially assigned extraordinary redshifts from imaging and then moved closer after spectroscopy. That process was not evidence that Webb had failed. It was the normal progression from candidate selection to confirmation. Deep imaging is designed to cast a broad net. Spectroscopy then asks whether the source contains features at exactly the wavelengths required by the proposed distance. Webb's near-infrared spectrograph is central to this work because it can divide faint infrared light into a spectrum rather than treating each filter as a single brightness measurement. A spectrum may reveal emission lines produced by ionized oxygen, hydrogen, or other elements. It may show a sharp break associated with absorption by neutral hydrogen between the galaxy and the telescope. Once the rest wavelength of a feature is known, its observed displacement gives a much stronger redshift measurement. When several features agree, the case becomes stronger still. This is why spectroscopically confirmed objects such as the highest redshift galaxies carry more scientific weight than unconfirmed candidates, even when a candidate appears to lie farther away. The same caution applies to stellar mass. Early reports sometimes described galaxies whose inferred masses seemed uncomfortably large for the young universe. Those masses were not placed on a scale and measured directly. They were reconstructed from the amount and color of the observed light using models of stellar populations. If an active black hole contributes to the luminosity, the galaxy can appear to contain more starlight than it actually does. If emission lines strongly brighten particular filters, the continuum can be overestimated. If dust alters the spectral shape, age and mass can become entangled. Better spectroscopy can separate these effects and often reduce the range of plausible interpretations. Some of the most extreme early mass claims therefore became less dramatic as data improved. Yet this correction did not make the broader Webb result disappear. Secure observations continued to show that luminous galaxies exist very early, and that some of them form stars efficiently enough to challenge earlier expectations. The scientific tension survived because it was never dependent on the most sensational candidate. What changed was its location. Instead of a crisis in the basic age or expansion history of the universe, the problem became one of galaxy formation efficiency, stellar populations, feedback, and the connection between visible galaxies and the dark matter halos containing them. This distinction is important because cosmological models are layered. On the larger scale, the standard model describes the expansion history, the proportions of ordinary matter, dark matter, and dark energy, and the growth of structure from small early density variations. Galaxy formation models then attempt to follow what ordinary matter does inside that framework. Gas cools, collapses, forms stars, is heated by radiation, is expelled by stellar explosions, flows back inward, enriches itself with heavy elements, forms dust, and sometimes feeds black holes. These processes occur on scales far smaller than the universe represented in a cosmological simulation, so they must often be approximated through carefully calibrated prescriptions. Webb is now observing exactly the era where those prescriptions were least directly tested. A mismatch can therefore expose weak assumptions without requiring the underlying cosmology to be discarded. An analogy is unnecessary because the distinction is already physical. Dark matter may predict how many halos of a certain mass should exist at a given time, while baryonic physics determines how bright the galaxies inside those halos become. If early galaxies convert gas into stars more efficiently than assumed, a survey can find more bright objects without there being more dark matter halos than cosmology permits. If young stars produce more ultraviolet radiation for the same stellar mass, the galaxies can again appear brighter. If star formation occurs in short bursts, a population can temporarily populate the luminous end of a survey more strongly than a smooth model predicts. Each solution changes the astrophysics while leaving the larger framework intact. There are still boundaries that matter. If observations eventually established far more massive galaxies than the available halos could plausibly contain, or found secure structures at times before the framework allowed them to form, the pressure would move deeper. Science does not protect a cosmological model from evidence. The point is simply that Webb has not reached that level of contradiction. Current tensions are being tested through better spectra, larger survey areas, improved simulations, a more careful separation of stellar and black hole light. Even the most interesting discrepancies are therefore treated as measurements to understand rather than declarations that cosmology has collapsed. This measured approach can sound less dramatic than the headlines, but it is scientifically more consequential. A model that broadly succeeds can be refined only when observations reveal where its approximations fail. Webb is providing that leverage. It is forcing theorists to ask whether star formation becomes unusually efficient in dense early environments, whether feedback behaves differently when galaxies are extremely gas-rich, whether the first stellar populations are more luminous than later ones, and whether rapidly growing black holes contaminate estimates once assigned entirely to stars. Each answer can alter the predicted appearance of the cosmic dawn. The result is not a universe without the Big Bang. It is a Big Bang universe whose first galaxies may develop through pathways that were previously oversimplified. That leaves the deepest Webb discoveries in a more interesting position than either certainty or collapse. Some early candidates have moved closer, some extreme mass estimates have fallen. Other galaxies have survived spectroscopic scrutiny and remain genuinely early, bright, and difficult to reproduce in detail. The data are becoming less sensational and more constraining at the same time. As the uncertain cases are removed, the remaining tension becomes harder to dismiss because it rests on stronger measurements. What Webb is challenging, then, is not the existence of a hot, expanding early universe. It is the assumption that the visible structures inside that universe had to grow as slowly as many earlier models expected. The models now under the greatest pressure are not the ones that describe an expanding universe beginning in a hot, dense state, but the ones that attempt to describe how ordinary matter behaves once it begins collecting inside the first dark matter halos. That distinction places the Webb results in a useful scientific frame. The large-scale structure of the universe can remain broadly consistent with standard cosmology, while the internal physics of young galaxies turns out to be faster, more efficient, or more variable than expected. The challenge is concentrated in the conversion between invisible gravitational scaffolding and visible galaxies. Dark matter provides most of the mass that shapes the halo, but stars form from baryonic matter, the ordinary gas that can cool, collide, radiate energy, fragment, and respond to feedback. The earliest galaxies therefore depend on a chain of processes that is difficult to simulate perfectly, especially at the tiny physical scales where individual clouds collapse compared with the immense volumes needed to model cosmic structure. One of the first quantities likely to require adjustment is star formation efficiency. A dark matter halo may gather a substantial reservoir of gas, yet only part of that gas becomes stars. In many models, feedback prevents the conversion from becoming too efficient. Newly formed massive stars emit tense radiation, drive winds, and later explode as supernovae, injecting energy into the surrounding gas. In a shallow, gravitational potential, that energy can heat material or push it out of the galaxy entirely. The result is a natural regulator. Star formation produces the processes that eventually slow further star formation. Webb suggests that this regulation may operate differently in some early systems. If gas is entering a young halo rapidly enough, the supply may temporarily outrun the ability of feedback to remove it. Dense regions can then convert gas into stars during short but powerful episodes, producing galaxies much brighter than a model based on smoother, less efficient growth would predict. This does not require every early galaxy to be unusually productive. Even a minority undergoing intense bursts can strongly alter the bright end of the observed population. The timing of feedback may therefore matter as much as its total strength. A model that assumes stellar energy couples immediately and efficiently to surrounding gas may suppress star formation too early. In reality, gas can be clumpy. Radiation can escape through low-density channels, and dense clouds may continue collapsing even while other parts of the galaxy are being heated. The geometry of the interstellar medium becomes important. Feedback can regulate a galaxy without acting as a single uniform break. Dust introduces a second uncertainty because it changes both the physical state of gas and the way a galaxy appears. Dust grains absorb ultraviolet light, shield molecular gas, provide surfaces for chemical reactions, and re-radiate absorbed energy at longer wavelengths. The first galaxy should begin with very little dust because the heavy elements needed to build grains have not yet been produced in large quantities. Yet massive stars evolve quickly, and supernovae can begin enriching their environments within a short time. Some early galaxies may therefore manufacture dust rapidly, while others remain relatively unobscured. That diversity affects inferred masses and star formation rates. A galaxy with little dust can appear extraordinarily bright in ultraviolet light because much of its stellar radiation escapes. Another with similar star formation activity may be dimmer because dust hides the youngest stars. Models that assign too simple a dust history to the early universe can therefore misjudge how many galaxies should cross an observational brightness threshold. Stellar populations themselves may also differ from those used to calibrate many later universe models. Stars forming from metal-poor gas tend to have different temperatures and spectra from stars born from chemically enriched material. If early stellar populations contain a larger fraction of massive stars, then a given amount of newly formed stellar mass can produce more ultraviolet radiation than expected. This possibility is especially important when converting observed light into a star formation rate. The conversion is not universal. It depends on the distribution of stellar masses, the metallicity, the age of the population, and how long star formation has continued. The first generations of stars may occupy an extreme end of this range. Population 3 stars, formed from nearly primordial hydrogen and helium, are expected to differ substantially from later stellar populations, although direct observational confirmation remains elusive. If traces of such populations contribute to very high redshift galaxies, then the luminosity per unit stellar mass could be higher than assumptions derived from nearby galaxies suggest. That would make some early systems look more massive or more productive than they truly are if the wrong stellar template is applied. Gas accretion is another area where the models may need greater flexibility. Early halos are embedded in a universe with high average density and rapid structural growth. Gas can flow along filaments of the cosmic web into young galaxies, sometimes remaining cool enough to penetrate deep into the halo. These inflows provide fuel for both stars and black holes. If simulations underestimate how effectively gas reaches dense central regions, they may underestimate the pace of visible growth. The effect can be amplified by mergers. Small galaxies collide frequently at high redshift, redistributing angular momentum and driving material inward. What appears observationally as a remarkably efficient galaxy may therefore be the temporary consequence of a larger environmental network feeding it from several directions. A successful model must reproduce not just average galaxy properties, but the full range of environments that Webb samples. The connection between baryonic matter and dark matter is especially important here. The number and growth rate of dark matter halos set an upper framework for what galaxies can exist. Ordinary matter cannot simply form massive galaxies without sufficient gravitational structure to contain them. But the fraction of a halo's baryons that become visible stars can vary dramatically. If early galaxies reach higher conversion efficiencies than expected for limited periods, the same halo population can produce more bright objects without altering the fundamental dark matter model. This is why the Webb tension often appears at the level of a galaxy formation rather than cosmology. The halos may be present in roughly the expected numbers, while the galaxies inside them become luminous sooner. Black holes add yet another variable because they can both imitate stellar light and change the evolution of the host. An accreting black hole can contribute strongly to the infrared and optical emission used to estimate galaxy mass. If that contribution is mistaken for starlight, the host can appear more massive than it really is. At the same time, radiation and outflows from the black hole can heat gas, remove material from the center, or alter where stars form. In some early systems, black hole feedback may begin before the galaxy reaches the mass at which such effects are most familiar in the later universe. Models that treat black hole growth as a secondary process, beginning only after substantial stellar assembly, may therefore miss an important route through early evolution. The little red dots and overmassive early black holes make this possibility difficult to ignore. Another adjustment may involve variability itself. Galaxy formation is often summarized through average relations between halo mass, stellar mass, and star formation rate. Those relations are useful, but the cosmic dawn may be especially bursty. A galaxy can brighten rapidly when fresh gas reaches the center, then fade after massive stars die or feedback disrupts the fuel supply. Two systems with similar total mass can therefore look very different depending on when they are observed. Webb selects galaxies through their light, so it naturally notices the active phases. If models assume smoother star formation histories, they can underpredict the number of luminous systems even when the long-term average amount of stellar mass is correct. This may be one of the simplest ways to reconcile part of the discrepancy without demanding extreme permanent efficiencies. Yet every proposed adjustment must survive other measurements. Increasing star formation efficiency cannot produce more stellar mass than the available baryons permit. Reducing feedback too strongly may create galaxies that become overly massive later. Changing the stellar mass distribution alters chemical enrichment and supernova rates. Increasing black hole activity affects radiation fields and reionization. The model is a connected system. Solving one discrepancy can create another. This is why the Webb results are valuable even when they do not overthrow the larger cosmological framework. They force galaxy formation theories to become more internally consistent under conditions that were previously only weakly observed. The first billion years now contain enough direct evidence to test assumptions that once remained hidden inside simulations. A successful picture will need to explain bright galaxies, rapid stellar assembly, early quiescence, complex structure, compact active nuclei, large black holes, and the changing ionization state of intergalactic hydrogen without treating each result as an isolated exception, the likely outcome is not a single dramatic correction. It is a more detailed description of how several known processes behave when gas fractions are high, metallicities are low, densities are greater, mergers are common, and the available time is short. The broad cosmological stage may remain the same while the actors move across it much faster than expected, and once those rates are recalibrated, the final frontier becomes clearer, whether Webb will continue finding familiar physical processes operating earlier and earlier, or eventually reach an epoch where even the first recognizable galaxies have not yet had time to exist. Beyond MOMS 14, the remaining distance to the first luminous structures is no longer an abstract gap measured only by theory. It is becoming a narrowing observational frontier. Each new Webb survey pushes into slightly earlier cosmic time, where galaxies should become rarer, smaller, less chemically enriched, and increasingly difficult to separate from the first generations of stars that preceded them. The significance of moving beyond a redshift of 14 is therefore not simply that another record may be broken. The deeper goal is to identify where recognizable galaxy formation gives way to something more primitive, isolated clusters of primordial stars, unstable gas concentrations, and the earliest black hole seeds assembling before familiar galactic structure has taken hold. MOMSI 14 already demonstrates that a luminous galaxy can exist when the universe is roughly 280 million years old. That observation immediately implies an earlier history. The stars responsible for its light must have formed before the moment Webb sees. The gas needed to produce those stars must have collapsed earlier still. The dark matter halo containing the system must have begun growing from still smaller fluctuations. Even the most distant confirmed galaxy is therefore not the beginning of the story. It is evidence that the beginning lies farther back. The remaining interval is narrow in cosmic terms, but scientifically it contains several of the most important transitions in astrophysics. Somewhere inside it, the first long-lived dark matter halos become capable of gathering enough gas for efficient cooling. Somewhere inside it, the first stars ignite from material containing almost nothing heavier than hydrogen and helium. Somewhere inside it, the first stellar explosions begin enriching that gas with carbon, oxygen, silicon and iron. Somewhere inside it, the first black holes appear. The order and spacing of those events determine what the earliest observable galaxies should look like. Webb is approaching the point where those theoretical stages may begin leaving direct signatures. One of the most sought-after signatures belongs to population 3 stars. The proposed first generation of stars formed from nearly primordial material. These stars have never been securely identified as an unambiguous population. Their existence is strongly expected because some first generation of stellar objects must have formed before heavy elements became common, but their exact properties remain uncertain. Many models suggest that low metallicity gas in the earliest halos may favour unusually massive stars, because without heavier elements the gas cools and fragments less efficiently. Massive population, 3 stars would burn hot, emit strong ultraviolet radiation, and live only briefly before ending in powerful explosions or collapsing into black holes. Their short lifetimes are one reason they are difficult to find. By the time a galaxy has undergone even modest chemical enrichment, the conditions for forming a purely primordial population may already have disappeared. Webb is therefore searching for an exceedingly narrow phase in which a system is luminous enough to detect, but still chemically primitive enough to preserve the signature of first-generation stars. Spectroscopy is central to that search. A genuinely primordial stellar population should produce a distinctive radiation field and unusual relationships among emission lines, especially in gas containing almost no heavier elements. Yet interpretation will remain difficult because young metal-poor stars from later generations can imitate some of the same features, and active black holes can introduce additional hard radiation. A convincing detection will likely require several lines of evidence pointing in the same direction rather than a single unusual spectral feature. The same problem applies to the first black holes. Webb has already found rapidly growing black holes at surprisingly early times, but those are not necessarily the first seeds themselves. A black hole observed hundreds of millions of years after the Big Bang may already have experienced many episodes of accretion and perhaps mergers. The earliest seeds could be far smaller and much fainter. If they begin as stellar remnants, their light may be almost impossible to separate from the young star clusters around them until accretion becomes intense. If they begin as heavy seeds formed through direct collapse, they could become detectable sooner, especially if a dense gas supply produces a luminous accretion disk. Finding a black hole close to its birth would provide one of the clearest tests of competing seed models. Its mass, host galaxy, chemical environment, and accretion state could show whether the object began small and grew rapidly or began already massive. The difficulty is that the earlier sources are intrinsically faint, while their light is shifted to increasingly long wavelengths. Webb can continue gaining depth through long exposures, but exposure time alone does not remove every limitation. The telescope has finite collecting area, background noise, and wavelength coverage. At extreme redshift, important spectral features move toward or beyond the regions where its instruments are most sensitive. The first stars may also form in systems too small to detect individually unless gravitational lensing magnifies them. Massive foreground clusters can act as natural telescopes by bending and amplifying light from objects behind them, allowing Webb to probe sources that would otherwise remain invisible. That benefit comes with complexity because lensing distorts images and requires detailed models of the foreground mass distribution to reconstruct the true brightness and shape of the background source. Blank field surveys avoid those specific lensing uncertainties and provide cleaner population statistics, but they cannot reach quite as faint for the same observing time. Both approaches are necessary. One reveals individual objects near the detection threshold, while the other measures how common different kinds of early systems are. Population is the key word, because the deepest scientific question cannot be answered by a single extraordinary galaxy. If Webb finds one object beyond MOMSI 14, it establishes that galaxy formation can reach that epoch. If it finds dozens, the implication changes. The early universe would then contain a substantial population of luminous systems, forcing models to reproduce not only an extreme exception, but a broader statistical pattern. The same logic applies to black holes and candidate primordial stellar populations. Rarity can often be explained through unusual environments. Abundance requires a more general mechanism. Webb's expanding sample will therefore reveal whether the objects currently described as shocking are genuinely exceptional or merely the first visible members of a once-hidden population. This distinction may ultimately resolve much of the tension created by the telescope's earliest results. Before Webb, observations of the cosmic dawn were strongly limited by sensitivity. A model calibrated against the few galaxies then known could naturally underestimate populations that remained below the detection threshold. Once Webb opened the infrared window more deeply, the universe did not suddenly change. The observed sample changed. Some of the apparent surprise may therefore reflect the difference between what existed and what earlier telescopes were capable of finding. Yet even that explanation has consequences. If luminous galaxies, compact active nuclei, and rapidly evolving systems are simply common features of the early universe, then models must reproduce that commonness. The discoveries would become less anomalous individually while becoming more important collectively. The frontier will also move toward a point where direct galaxy detection becomes fundamentally harder because the objects themselves have not had enough time to build large stellar populations. There should be an epoch when the typical luminous source is no longer a galaxy containing many generations of stars, but a much smaller system in the earlier stages of collapse. Approaching that boundary would change the nature of Webb's discoveries. Instead of asking why a young galaxy appears too mature, astronomers would begin asking whether a faint source is a galaxy at all. It might be a compact star cluster. It might be a proto-galaxy dominated by one brief burst. It might be an accreting black hole embedded in almost pristine gas. The categories used for later cosmic history may begin to blur because the structures being observed have not yet separated into their familiar forms. This is where Webb may reach its most important limit. The telescope does not need to see the very first star directly to transform the understanding of cosmic dawn. By mapping the earliest galaxies ever observed, measuring their chemical state, tracing their ionizing radiation, and identifying the oldest black holes within reach, it can surround the unseen beginning with increasingly tight constraints. The first stars must form before the earliest enriched galaxies. The first black hole seeds must appear before the quasars that later become massive. The first ionized bubbles must emerge before reionization becomes widespread. Every confirmed observation moves one boundary closer to those hidden starting points. MOM-Z14 therefore may not remain the record for long, but its eventual replacement will not make it less important. It marks a stage in which the observable universe has already become rich enough to test processes that were once entirely theoretical. The next objects may lie earlier, fainter and closer to the transition between darkness and sustained starlight. Some may force another revision in star formation efficiency. Some may reveal a first clear signature of chemically primitive stars. Some may expose black hole growth at an even earlier stage. Others may simply show that the universe was producing recognizable galaxies earlier and more routinely than previous surveys could demonstrate. That final possibility carries a quieter kind of surprise. The most startling objects found by Webb may turn out not to be cosmic accidents at all. They may be ordinary representatives of an early universe that was always more productive, more structured, and more rapidly evolving than observation had previously allowed astronomy to see. The farther Webb reaches into the early universe, the less the story resembles a sequence of impossible discoveries, and the more it becomes a gradual redrawing of what early cosmic growth could accomplish. Galaxies appear bright when there has been little time to build them. Some gather substantial stellar populations rapidly. Others develop disks, dense cores, and concentrated regions of star formation while the universe is still young. Compact red sources hint that black hole growth may already be woven into the first stages of galactic evolution, and the radiation from early stars begins clearing neutral hydrogen from the space between galaxies. None of this removes the larger cosmological framework that gives these observations their meaning. Instead, it places pressure on the details: how efficiently gas cools, how quickly stars form, how feedback regulates young systems, how black holes acquire their first mass, and how much variation can exist from one early environment to another. MOM-Z14 stands near the present observational edge, but the events required to create it begin earlier than the light now being measured. Beyond it lies a diminishing interval containing the first sustained star formation, the first enrichment of primordial gas, and perhaps the first black hole seeds. Webb may eventually detect objects closer to those transitions, or it may reach a point where individual sources become too faint and too primitive to classify cleanly. Either outcome would be informative. The deepest observations do not need to uncover something that overturns everything known in order to matter. Their value comes from giving previously invisible epochs measurable form. What once existed mainly inside simulations is becoming a collection of spectra, redshifts, masses, structures, and uncertainties. And as those measurements accumulate, the early universe seems less empty than expected, less slow in its development, and far more capable of building complexity within remarkably little time. The remaining mystery is quieter now, but sharper, not whether the young universe could form structure, but how